All right, thank you for having me, inviting me. I'm excited to talk a bit about my work and my lab. My name is Ral Bielawski. I'm an assistant professor in mechanical and aerospace engineering, and I sort of recently finished my Ph.D. from the University of Michigan, where I sort of studied multi-phase and reacting flows, and I'm taking some aspects of that work and sort of expanding and growing it here at UCF. So very broadly, I use high fidelity numerical simulations to study sort of hypersonic systems, flows, and regimes. A little more specifically, I sort of leverage the recent advances in computing to explore a sort of an extreme range of length scales. And this has really only been made possible by recent advances in GPU computing. And then I tend to apply that to propulsion applications for hypersonics and more specifically detonation engines. So our traditional combustion engines, our traditional combustion process use something called a deflagration. A detonation is sort of a much more compact, more rapid form of combustion that occurs sort of on the order of millimeters and travels sort of thousands of meters per second as opposed to tens of meters per second. And so this is sort of very advantageous for hypersonics or anywhere you want to fly, because one, it's a smaller, lighter system. So if you're putting something that needs to sort of generate lift, you want it to be as light or small as possible. And two, because of the more rapid combustion, there's potential for it to operate at much higher sort of velocities in the system, which is a critical problem for hypersonic propulsion, because if you have flow traveling at Mach 5, Mach 6, you have very little time to actually mix and burn and then turn that sort of combustion to useful thrust. A second sort of aspect is on liquid fuels or multi-phase flows. And these are sort of very synergistic because practical systems are going to have to use liquid fuels, as liquid fuels have a higher energy density compared to their gaseous counterparts. And it's already difficult enough to generate a hypersonic system, so to generate a practical system, liquid fuels will be critical. Now, I mentioned that you had these very short time constraints. Now, before you can use fuel, you have to get it into a vapor phase and mix it before you can burn it. So the presence of liquids further complicates this challenge, as you need to first break up, evaporate, and mix, as opposed to just sort of mixing for gaseous fuels. And so I'm going to talk a little bit about one area of research in particular I do, give you a bit of a deep dive on how you can use these high fidelity simulations to get a bit more understanding, and then how we can use that to drive sort of engine development and design. So a big area of work I've worked on is shock or detonation driven breakup of liquid droplets. So an appealing idea is to use the shock waves or detonations found in these hypersonic systems to actually accelerate the breakup evaporation of your droplets, potentially mitigating this challenge of using liquid fuels. And so you can see sort of a video here of a droplet that's sort of simulated that is being shattered by a shock wave. And we can run a wide range of conditions and configurations. And we find that there's actually sort of a similar set of sort of stages to the breakup, and we can understand what are the driving processes of each of these. And so I have a schematic here that's easier to understand of sort of a droplet that's been subject to either a shock or a detonation. It's sort of a spherical. It's then exposed to sort of the very high aerodynamic pressures, which leads to this sort of flattening, which is sometimes termed pancaking of your droplet. While this is going on, you see this generation of surface instabilities due to either Rayleigh-Taylor or Kelvin-Helmholtz instabilities. And then when your droplet has sort of been flattened sufficiently, that sort of the thickness between the front and the back of your liquid is comparable to that of your sort of instability size, it suddenly and rapidly undergoes this sort of piercing event that sort of happens repeatedly until you're left with these sort of very small droplets. And so we can use our high fidelity simulation to sort of extract out what are maybe the controlling processes that help us inform sort of model development. And so if we look at this process and then try to think about what we care about here, what we're caring about for combustion applications is how can we get this to evaporate? So we're really asking what fraction of the mass is contained in these small droplets that can evaporate rapidly compared to a fraction of masses in your large droplets that you effectively cannot evaporate. And we can see that there's actually this delay that relates to this time to current piercing to occur. And so at the beginning, shortly after the sort of the shock wave or detonation hits, there's almost no small droplets and therefore no vapor or fuel available to burn. And this really helps to sort of inform or help, we think will help to inform what size of droplets you can actually use in detonation systems, and might actually be a sort of a key parameter for what, how much do we have to break up our droplets before a shock or a detonation hits them. Now, what's really important is actually capturing what is the distribution, the size of droplets throughout this sort of breakup process. And this is very hard to do experimentally at relevant conditions because it's very hard to generate the relevant conditions. And then due to the high speed, high temperature, and high pressure, a lot of imaging techniques are sort of unable to have the required resolution, or it's very difficult to generate them. So numerically, we're actually able to capture this sort of distribution. And this distribution informs the rate at which you evaporate, because only these small droplets are the ones that sort of are available to become vapor. However, this is one of the areas where we have sort of the most uncertainty, because breakup is a molecular process. Sort of that interface of when you go from one droplet to two occurs at the interface at a molecular scale. And so this is one of those areas where we're going to need sort of continued exploration, continued advancement, likely through a larger multidisciplinary team, combining experiments and a wide range of different simulation techniques to sort of really gain even more confidence. But we at least now have sort of a foundation where we have some understanding of the process, some potential distribution that we can then apply to sort of larger engine scale simulations. In addition, we can look at sort of other features of this process, particularly for detonation-induced breakup. There is evaporation. And so you can see in the top right there that these evaporation curves for the black lines are for the simulations, that there's this delay where there's really no evaporation occurring. And this again comes back to what we saw before we got from our qualitative understanding that there's a delay before small droplets are generated. And then it now evaporates as if it was a smaller droplet. And that is again due to the fact that what is evaporating are the smaller droplets. And they're what leads to this sort of sudden increase. And so we have some sense that we can actually do we have some model that handles the breakup, heat transfer, and evaporation. But going forward, if we look at sort of that bottom right, that's a detonation breaking up of water droplet. The top half is temperature, the bottom half is vapor. The blue region represents very cold regions full of vapor. And it is not well mixed. There's a lot of stratification. And it's not clear how to incorporate that sort of delay in mixing or unmixedness or stratification into these models. And that may actually start to become maybe a critical parameter that is necessary for understanding maybe the structure or stability of multi-phase detonations, which are a critical technology for hypersonic propulsion. Going forward, I'm going to sort of continue this work at sort of a very small scale, looking at individual droplets, but trying to couple them where there are clouds or collections of droplets, and try to understand that process and structure of a detonation that is consuming and operating on liquid fuels. And then combining that with sort of engine scale studies using those models to try to look at a detonation engine. So you can see an example here in the top, the right there of a leak detonation engine and a simulation that was done for gaseous fuels. And there's desire to progress to sort of look at what is the stability and understanding the sort of multi-phase version. In addition, this work is really enabled by the drastic increases in computing that have occurred in the last decade. When I finished my undergraduate, a million cells was an expensive computation, but routine. Now, 100 billion cells is expensive, but routine. And in the future, 1 billion cells and more is going to sort of become a routine thing we can do academically. But this is only possible if you can continue to leverage the advances in computing. And often that comes through new architectures and heterogeneous computing. And so understanding how our CFD algorithms can effectively be implemented and used on these systems enables us to sort of continue to push the length of length scales and study problems that 10 years ago were considered inconceivable due to the required cost and configuration. Thank you for listening to the presentation. If you have any questions, I'd be happy to answer them.